All right, welcome back. Let's recap what we learned in the last two videos. So here's a recap of what we learned from the last two examples. We will use these lessons in the rest of the chapter when we construct and study inverse functions for sine, for tangent, and for cosine. All right, so assume that f of x is the inverse of a function g of x. Then f of x equals y exactly when y equals x equals g of y. So when you send the f to the other side, it becomes g. Then we saw that if you apply f and g one after the other, then they cancel out and you get x back. Whether you apply f first, like we did over here, or when you apply g first, like we did over here. We also saw that the graph of f of x is obtained from the graph of g of x by reflection on the line y equals x. So that's the same thing as switching the order of x and y. So switching x and y. So if you had 2, 5, then you'd have 5, 2. And then the domain of f of x is the range of g of x. The range of f of x is the domain. So the domain and the range are flipped when you go from a function to its inverse. All right, so using that, we'll have an official definition of an inverse. Definition 1.1.1, a function f is the inverse of a function g if f composed with g. So that means you apply g first, then f, that would be equal to x. And the same thing if you apply f first, then g. And that's true for any x in the domain of g for the first one, and for any x in the domain of f. So any x in the domain of the first function you apply. In which case, we write f of x is equal to g inverse of x. All right, so let me do an example. For a function g of x built up of many different functions, we can sometimes find an inverse as follow. You start with y equals g of x, and then you isolate x, and you get that x equals g inverse of y. Some high school, it depends on the teachers, would start with x equals g of y, and then would isolate y, and you would get that whatever your y isolate x. No, isolate y, sorry. It's just confusing side by side. Whatever your y was equal to, that would be your inverse function. So what's nice about this way of doing it is that you do end up with x as a variable. I like this because when we talk of inverse trig functions, the two sides will have different variables. One will be an angle, one will be a value, so we'll be using different letters. And so I'd rather you get used to not changing them, but both are fine. I will accept both for sure. All right, so let's try this example. I'm giving you a function. So example 1.1.3, find the inverse of the function g of x equals ln of cube root of 4x minus 2. And so I'm going to start with y equals g of x, which is equal to ln a cube root of 4x minus 2. Then I would apply the exponential to both sides. That's the inverse of the log. So I always take the inverse of the outermost function. And that's going to cancel with the log, and I'll get cube root of 4x minus 2. Then I want to cancel with the minus 2. Well, the inverse function would be plus 2. And so I get ey plus 2 is equal to cube root of 4x. Now the outermost function is the cube root, and so you would cube both sides. You will get ey plus 2 cubed equals 4x, and then you would divide by 4. And so, sorry, I'm a bit low on space. Let me do it over here. And then you divide by 4, and you get that ey plus 2 cubed divided by 4 is x. So I have accomplished what I was looking to do. I isolated x, and then whatever I get, the value that I get for x, that's the inverse function applied to y. So g inverse of y equals ey plus 2 cubed divided by 4. And if you wanted to use x as your variable, you just replace y by x. You could do it at the end, like some high school teachers. Anyways, sorry, my English sometimes slips. You could do it at the start.